everyone. So let's get started for our control seminar today. So I'm very pleased that we have Dr. Young from Northeastern University, who actually is no stranger to Ann Arbor because he spent 10 years ago, sometime as a postdoctoral researcher. He was working with Nejmi USA back then. After that, he started his faculty career at Arizona State University, and a couple of years later, he moved to Northeastern, where he's currently associate professor in mechanical engineering. With Young, we have worked together since his time in Michigan and thereafter, and he has been very successful in his faculty career so far. I was looking up his awards. He has a Dartmouth Faculty Award, a Career Faculty Award, a NONR, a Young Investigator Award, another one which I don't remember right now, but I think there were 4. The NASA one, the NASA Early Career Faculty Award, as well as the George Saridis Best Transactions Paper Award. So his research has been focusing on control estimation, planning and learning with applications to autonomous robotic and cyber physical systems, with emphasis on safety, resilience, and robustness. And with that, please join me in welcoming him and hearing more about his work. So thank you.
Thank you for the kind introduction, and thank you for inviting me back here. It's great to, I guess people can hear me a bit loud. Yeah, it's great to be back here after almost 10 years now, and really good memories. I was here in the X building, just right here. It's been a while, so it's nice to be back and to be able to get this up. It's turned on.
Thank you, on.
Okay. Yeah, great. I can hear the echo actually of myself. Okay, so yeah, I'm currently at Northeastern University, and I guess in the mechanical engineering department, and I'm here to talk to you a little bit about my research. I guess my research, I dabble in a lot of different things, and this is just some of the things that we've been working on, and I'm excited to talk about specifically how to do in things with, wait, I guess this was a wrong title that I have here, but anyway, I guess it's related to interval bounding via mixed monotonicity, and it's related to some kind of learning as well as set valued observers. Okay, so let me see, can I switch my screens? All right, so yeah, I guess my work has been mainly, I would say, motivated by just cyber physical systems, or just autonomous systems that are safety critical, just like your autonomous car, power system, medical system, whatever it is. There's some element of safety that we care about, and we want to make sure that things that have bad consequences, catastrophic consequences don't happen. And that's kind of what I would consider kind of the motivation for my research. And I think that there are several challenges for safety, and one big one is that of model discrepancies. So that includes, I guess, if you have changes or parametric uncertainties, like your mass of your rocket might have been different from what you expected, or you're in the passenger car and a different person sits in it and you have a different mass. So these are things that you might not know them exactly. And even if you were to train your models based on data, there might be some issues with generalization errors that you have to deal with. So I care about, these are some challenges that could cause us to not be able to say that much about safety. And there's also issues of partial and uncertain information. So we might not measure all the states, we might be dealing with other agents, we might not have all the information. We might have data that's noisy, we might have occlusions, we might have delays, and so on and so forth. And those are not intentional, I guess, not exactly intentional, but they could also be intentional cyber attacks on systems that causes, I guess, someone trying to game the system and try to cause collisions in cars and things like that. So these are all at least some of the things that I consider would be issues that we will have to handle if we want to really deal with safety. And today I will be mainly focusing on the modeling discrepancies type part of the problem, and thinking about problems that have uncertainty in terms of parametric uncertainty, measurement uncertainty, as well as maybe generalization errors when it comes to data-driven models. So I guess when we deal with uncertainties, I like to think about that there being two separate or kind of separate approaches to dealing with that. One is more of a stochastic approach or stochastic way of describing uncertainty, and one that is more robust or more guaranteed type of approach, where in a stochastic setting, people might characterize uncertainty using probability distributions, usually with some assumptions on knowing the probability distributions. And for more robust type of approach, or the way I categorize it, it's based on uncertainty that are characterized by sets. Some tolerance, some plus minus tolerance in terms of accuracy of where I am. Maybe I know where I am plus minus 2 centimeters. So that would be kind of an uncertainty of where I am, but described by sets. And I think that more stochastic type approach generally emphasizes best expected or average performance, whereas a robust approach, when we have bounded sets, we consider, or uncertainty, we would emphasize more on best worst case performance. And safety in stochastic type problems would usually be guaranteed based on some form of probability of collision or chance constraint, whereas safety for the robust approach, it's more about guaranteeing it in the worst case scenario, and that includes really rare events and corner cases. And I would say that for stochastic approach, the main engine that's the main engine behind a lot of machine learning, stochastic control, all type of problems. And for the robust type methods, I would argue that I guess ultimately we are dealing with sets, so it's kind of a set-based approach. And the set-based approach is kind of the topic that I will be focusing on, I'm focusing on in my research, as well as what I'm going to be presenting today. So let's talk about sets again, and why do we talk about sets? What are sets, and how? I'm guessing this might be familiar to maybe a lot of people. Generally, they appear very naturally in a lot of control systems design. So first of all, constraints are very naturally described as, I guess, as sets. This half of the room is a set where it's safe, and the other side of the room is not safe. And uncertainties, when you think about them as bounded uncertainties, or even unbounded uncertainties, but they have constraints on the type of uncertainties that you can have, that itself can be well described as sets. And even safety specifications or even task specifications can be also considered as sets. And when we talk about sets can be convex, they can be non-convex, they can be finite sets of sets, and there's different type of math operators that people have to compute with sets as opposed to just the normal arithmetic that people have. So what are some examples of sets? So we could have state or input constraints that's described by some sort of a polyhedron or the polytope that might look like that, some sort of a polygon in higher dimensional state space. And you might have input constraints, in this case, kind of a hyperrectangle or an interval, and we will be, or hyperrectangle or interval, which we will be focusing on quite a bit in this talk. Mainly because it has its good properties, and I will talk about them later. And we can also have bounded uncertainties, where zonotope is another type of representation that is usually written in that form. And you might have a hyperbole or hypersphere that you can have that is also a bounded set representation. And then I guess these temporal logic type specifications can also be thought about the set of behaviors that are acceptable, that you have to satisfy. And then you can also think about differential inclusions or hybrid systems as also having sets that are involved. So differential inclusions would be just basically the dynamics itself is itself a set mapping, and the set in which the domain in which I guess system dynamics apply for a switch system or a hybrid system itself is also a set. So set naturally happens, and I just want to argue that we we deal with that all the time, and so we want to be able to compute with them. And in terms of set-based methods in controls, I guess one that people might have seen quite a bit is just reachability-based type problems. So you want to do verification, you want to do planning. So instead of planning with just specific trajectories, you plan with sets of trajectories directly with sets. That's a problem of set value estimation, meaning that if I start from a possible initial set of where I am, if I have a dynamical system, how does my set evolve over time because of dynamics? And how do I compute with that? That's I would call set value estimation if I want to know what the state is of my system. There's also set-based control. So safety type controllers, including CBFs, kind of compute a safe region or safe set, and I have to remain within that set. And then there is also set membership type learning problems, where instead of trying to learn a specific function that fits all my data, I try to find a set of possible region for the function that captures or sandwiches my true function, so that is the set uncertainty that I have when I'm learning some sort of a function. And I will be talking about different aspects of all of this, or almost all of this here in this talk. So, okay. So let me start first with, let me actually, okay. So yeah, so there are a few things that I want to talk about. I guess the first thing I will talk about is just some techniques that I think would be helpful to just describe, and that relates to mixed monotonicity and also this interpolation type problems, and that we will build upon these techniques later on in part B and C, where we will talk about applying that for learning type problems with CBF for safety, as well as computing, doing set value estimation with observers. So if we have a function, if we only have a state as a single point of state, then the output itself of that function will just be f of x. If we have a point input, but we have a set value function, then the output will also be a set. If we have a set value input with a set value function, the output is still going to be a set. And then we start thinking about dynamical systems. If I have one specific input trajectory, I have one specific output trajectories. But if I have one set of input trajectories, but my system now is unknown, my parameters are unknown, my weight of the mass of my car might be between 1,000 to 1,100 kilograms or something, then you have a set behavior of what the system is going to be. And if you have now inputs to the system that might be disturbances that are also captured by sets, then you have to propagate it through an uncertain system, and then the outputs of them are still going to be sets. So basically, my whole point here is I just want to talk about why sets are important and why that happens very naturally, and we want to be able to capture sets that represents where our states could be or where our outputs of our systems can be. So some other operations that we have for sets are, I guess, Minkowski sums, affine map, intersection, and nonlinear maps. These are all operations that are related, or they're all, I guess, things that are common in dealing with sets. My main takeaway that I want to bring about in this slide here at the very least is just to say that for all these operations, if you, depending on what is the set that you start with, the output of that function, so we are talking about passing this through a function, if that function that we have is either Minkowski sum or affine map and so on, if you start with an ellipsoid, once you start computing with that, they might not actually end up remaining as ellipsoids, so you might have to over-approximate them sometimes. So that's where I'm trying to get to, and that if you start with intervals, or just hyperrectangles, then different types of operations, sometimes it's closed under the operation, it remains an interval, sometimes they don't. And what people would do is we'll try to bound them with another interval so that we have a way to capture and make sure that we can guarantee that the true behavior always remains within that interval or that box. And for zonotopes, which is another type of representation, some of the operations also are close, but not all of them. Whereas for polytopes, that's most of the operations or functions are going to make them still close in the sense that they will remain polytopes. But of course, if you have a nonlinear map, it will not be remain a polytope, but we want to kind of over approximate that with a polytope. So today, we will be focusing mainly on, why am I, it seems like I'm looking at the set of slides that's older version of what I have, but let's continue on and then hopefully it's the right one. If not, I have to switch quickly. Okay, so I guess, actually, give me a second. Let me stop sharing here. I think I might have opened the older file that looks more different than I expected. Oh, it's the same one. So it's fine. I guess I will just do that anyway. Okay. Sorry about that. Let me just continue from here. Oops. Okay. All right. So I'm just saying that today I will be focusing mostly on intervals, but it turns out that, I guess that's the part of my slide that is a bit weird, is that both zonotopes and polytopes are, you can think of them as related to intervals, but kind of in a lifted space, so that it's easier. If you can develop tools that you can compute with for intervals, then you can actually get the others sort of almost for free. And so I want to focus on interval bounding. I'm just not sure why my slides are not exactly what I was hoping for. But anyway, I guess interval arithmetic is something that you can have. It's just arithmetic that you have not on single values anymore, but on intervals. And these are things that you can find even on Wikipedia. I guess it's quite common these days that you can compute with interval arithmetic. And that includes exponential functions, logarithm, odd powers, and so on. You can do that for specific type of nonlinear functions. In general, when you have a nonlinear function, you cannot really bound the set that easily, or the output of the function, even if you give it an interval input to the function, then we will try to find a bounding box that kind of bounds it, and that is something we call an interval extension. And there are different types of forms that people have done in the literature. They are natural inclusion, centered form inclusion, and mixed form inclusion. But I want to present to you a different way of finding this inclusion function that's based on mixed monotonicity. And so I want to quickly present mixed monotonicity. I guess people in this here may have heard about it. I guess actually this paper is a paper from Professor Ozai from here, that basically says that if I have a function, we would call that function mixed monotone if you can define another function, which we call the decomposition function, that has twice the state space. And if it satisfies these three, if it's mixed monotone, if it satisfies these three properties. And the first property is that if I give it the same exact input to that function for that both arguments of that decomposition function, then I will recover the original function. So that's the first condition for mixed monotonicity. The second condition says that the function itself is going to be, when you fix the second argument, in the first argument is going to be monotonically increasing. And for the third condition is if you fix the first argument, it's going to be monotonically decreasing in the second argument. So that's basically what it is. If I have any function that's nonlinear, I would call it mixed monotone if I can find a decomposition function that satisfies these three properties. Okay, so why is this nice? It's nice because once you can write down a decomposition function, then you can bound a function from below and above. And this here would be just a box that kind of includes everything that's possible for this function by just choosing, I guess, the first element as the biggest value and then the second, the lower. So the x here is bounded by x under bar and x upper bar. And you just have to switch the order and you can directly get the bounds for the function. So this here is an inclusion function, and that you can directly use mixed monotonicity to do that. So how about dynamical systems? This is talking about functions. We just have a function, we can bound the functions. If we know what the input is an interval, the output is going to be this interval given by that. But what if it's a dynamical system? It turns out that we can also bound dynamical systems, and we can do it for both discrete time and continuous time systems. And this is just a collection of the different few definitions in different places. Essentially, what I presented with the properties of mixed monotonicity for a function that kind of applies directly for that function for the discrete time systems representation. But if you have a continuous time system, then the second condition, which is it being monotonically increasing in the first argument, gets slightly relaxed such that it doesn't include the terms that's on the diagonal. It's some details, but basically you can also have some conditions and call them mixed monotone. And what that tells us is that we can then use the decomposition functions and build what's called an embedding system. And actually that's a typo. This here should be FD and FD as well. So once you have the decomposition functions, you can write down this what's called an embedding system, which is the dynamics of the upper bound and the dynamics of the lower bound. And if you just run it through this embedding system, what we can guarantee is that if your states will always be bounded between the lower bound and the upper bound of the states for all times. So this here allows us to solve the problem of saying that now if I give it an interval initial state to my system, then my output of, my state in the future will always be bounded by a box itself or another interval, and the dynamics of that is given by the embedded system.
Yeah.
Yes. Yes.
So are decomposition functions like the FD, like a superscript and subscript, easy to compute or define given a system?
That's a very good question. That's the next thing that I'm going to talk about because I hope it's the next thing, I guess, because I got my things out of order. I got my slides out of order, but I will be talking about it, which is that, yes, the main question is if you have a function f, for what kind of function can I find a decomposition function? That's the first question. The second question is if I know that it exists, how can I compute it? Or is it easy to compute? Because if the computation to find it is just as hard as solving the problem itself, then there's really no point in using it. But we want to have a way to be able to compute it if we can, or if it exists. And for that, we need to know when it happened, when it exists, and how to compute that. But just want to finish up this slide just to say that I guess by construction, we can bound the states of the system from below and above by just running it through this embedding system. Okay, so this here is, it is the right slide to, actually, there's a missing slide. I'm not sure why. I'm not sure why is it that I'm having
your first slide actually said that you're giving this University of Water.
Okay, so that's the reason why, because I opened the wrong set of slides. Or I shared the wrong slide because I have both of them open. Okay, sorry. Okay, it's not the same. That's why it just makes it look like it's the wrong set of slides. But it's this one here. Okay. I'm sorry? Oh, it still says that, so that's the wrong one. Because I did present some version of this here over there. It's this one here. Okay, it does say Michigan there. Okay, but sorry, I just have too many things open usually. And I know it's recorded, so it's embarrassing, but okay. Let's share this first, and then let's try to go to this slide. That's the one that I have, and this is why it's been messed up. And I truly apologize for that. Is that the button that I'm looking for? Okay. All right. So same slide here. I guess we are trying to bound it. The question is, how do we find that? It turns out that people have been writing papers for finding how to find this decomposition function and when does it exist. And I just want to first start by just presenting a specific version of how to decompose it. And well, I guess, yeah. So the way that we started thinking about how to compute this function is we take the original function itself, we kind of decompose it into two parts, where one part of that function is what we call JSS function or JSS mapping, which means that the Jacobian matrix itself is sign stable, meaning for each element of the Jacobian, it's either the whole interval that's possible for that, it's either positive or negative. It cannot include zero, essentially. And then there is going to be a remainder term, which is a linear term that you can always construct. So whatever function, pretend that it is continuous for now, you can kind of decompose it into a component that's Jacobian sign stable and a component that is linear. And that you can do it very specifically with a specific linear remainder. You can always get it to be Jacobian sign stable if you know the bounds of the Jacobian of your function in the first place. And based on that, the linear function, it's pretty easy to just kind of bound them. That's a closed form expression for bounding the lower and upper bound, and they can be shown to be tight. And the second part of it is Jacobian sign stable. And the fact that it's Jacobian sign stable means that kind of the sign of the gradient, so to say. So then the maximum or minimum value can be found at one of the corner points. So you don't have to evaluate it over the whole domain. You have to only evaluate the corner points and just take the biggest value would be that and the smallest value would be that. Because it's a Jacobian sign stable function, the extremum will always be found at one of the vertices of the interval.
But
yes.
H there is not the Jacobian.
No, H is not the Jacobian. Well, let me start first by saying that the Jacobian of our function, we assume that it has bounds, so upper bound and lower bound for each element. We will use that upper bound and the lower bound to construct H. And then that H there is some version of the bounds on the Jacobian. And the other one automatically will, by construction, would be Jacobian sign stable. And this allows us to bound the two terms separately, and then we can combine them together and we construct this decomposition function. And this is our way of doing it, but I guess there are people that have shown that you can actually also just pose it as a nonlinear optimization problem, minimize the upper bound or try to minimize the upper bound on that function by just solving a nonlinear optimization problem, or to maximize the lower bound by solving another optimization problem. But that is something that you will have to solve a lot of nonlinear optimization problems at all times, which is something that is not easy to do except for simple problems or that for simple enough problems, you can even write down closed form solutions. But in general, I guess if you do this decomposition that we are proposing, then we can get these decomposition functions directly from just by construction. So that's one of the things that we've been doing. And what we could show is that the previous slide I mentioned that you have the H matrix that's based on the Jacobian bounds. And I have this symbol here for OR. So you can either do it based on the upper bound or the lower bound for each element, which means that there's actually a lot of different cases that you can have, but there's just going to be a finite number of them. And you don't have to find the minimum or the maximum of all of them, but if you do a few of them, then it will always be an upper bound or always be a lower bound. And so that's kind of our way of computing that. And we found that this here is kind of somewhat easy to compute. And we can show that for this remainder form type approach, it is the tightest type of decomposition function that we can find. And that actually includes the one from Professor Ozai's work, that they also have a way of doing it to construct the decomposition function. And it's actually, although they don't call it remainder form, it actually belongs to that family of remainder form decomposition functions. Yes?
Question from the chat, because it's relevant to this topic. So they ask, for boundedness of the Jacobians, do you assume that X varies within a bounded set?
Assume that what is in
the state X varies within a bounded set, if this is an assumption or not.
So that's a good question. So I guess you could have Jacobians that are bounded even not within bounded domains, or it could be an unbounded domain, but the Jacobians are bounded. There are functions that way. In that case, then I only need the Jacobian bounds. And but it's true that for certain functions that you have, the Jacobians might not be bounded in each direction. And generally, when we try to apply these kind of problems, we usually assume that we have a bounded state that we operate in, that we want to control our systems to stay within anyway. So then we just need the Jacobian bound to hold for that domain that we are interested in. So in some sense, yes, but in some cases, we don't even need that. So it's just for whatever domain that we are interested in, we just have to have the Jacobian bounds for that, and we can use that to construct that. And actually, the point here that I'm also going to make, but what I'm describing there is just one specific way of doing it, but it actually also applies to non-smooth functions as well as semi-continuous functions. So when I say that the Jacobians are bounded, we only actually need them to be, we only need the Clark, I guess, derivatives, I guess the gradients, to be bounded on one side. And that's the minimum that you need to be able to construct it the way we do. But in most cases, we just, for simplicity, we will just assume that we have the Jacobian bounds in every direction. But to really just do that method that we have, it only needs to be bounded on one side. And it could also apply to non-smooth functions. And at least for the examples that we've tried, the different inclusion function methods that I mentioned, using interval arithmetic, we found that our way of bounding it tends to outperform almost all of them. I mean, there are cases for which they are not, but we can always use both and use the tightest bound from both. So there's no problem at all. It's just an alternative method that you can have. And the other thing that we found that we think is helpful for doing analysis is that actually the upper bound and the lower bound of that inclusion function, it kind of satisfies some sort of a Lipschitz-like upper bound that allows us to do analysis. Okay. Why did it stop? Okay. All right. So this here is just to show very quickly what's.
You may want to move a little bit the wire. Sometimes it's
wire.
the USB-C plugged in.
The Zoom still.
But it's not showing here.
No, not showing.
What's happening?
We're missing today.
That is happening.
You think I'm plug and replug?
That would be the laptop, right? Yeah.
Okay.
Yeah, I'll switch over there.
So maybe just switch to the Zoom PC. Oh, okay. Okay.
There's some uncertainty in their system.
I guess height floating. Sorry. This is just a quick slide to show that you can apply that decomposition using the decomposition functions to just do reachability, where I guess we have a true function over time, and then we can always bound them. And these are using the different types of inclusion functions, and we can show that ours is kind of the tightest that you can get. And you can apply that to polytopes also, but I'm not going to go into the details of that. Okay, so that's the first part of the thing that I want to talk about, which is bounding functions. And I guess the other thing that now that I have my newer slides, I want to go back to a slide that was missing because I noticed it when I was doing it. And that is something, is another set operation that I want to briefly talk about because that will be part of one of the methods that we will be doing. And that is of what's called projection and lifting. So I talk about operations as just functions, but one thing that you can do with sets is that of projection. One is when you have a set given by this hashed set here. So if you have a point that's outside, you might want to project it onto that set. So that's an operation that you can do. And you can project it either orthogonally or you can project it in parallel to the other constraints, and you have certain functions that you can have or solutions to that. And there's also a way to just find the set of all possible projections, and that's given right here, and that is just a prelude to what I will be using it for later. But I want to use this here as the argument here to show that you can have projection of sets as well. So you can take a set, you can project it down to a lower dimensional space, so that we will call a projection. But there is also the way of actually lifting from a lower dimensional set to a higher dimensional set. And the reason why I wanted to talk about that was to justify why I said that everything that we do for intervals can also apply to polytopes, because it turns out that polytopes or polyhedrons, or polytopes specifically, that can be described by this hyperplane representation, Px less than equals to Q, has been shown by some paper that it can be represented by what's called a constraint zonotope. So this is a center, these are generators, and is this new variable here is the generator variable, and this generator variable itself is an interval. So basically what this here is saying is that you can take any polytope and represent it into something that has generators that are intervals and with some additional constraints. So we can think about polytopes as lifted intervals with constraints. And that's why it's easier to deal with once you do, I saw you, I will get back to you. Once we can compute with intervals, then we can naturally extend that to polytopes as well. Yes?
Do you think of it, you could like height, it's like a gradient, color gradient from 0 to 255, like seeing like a picture or a video, if you're changing over time?
I haven't really thought about that, but I imagine that that might be possible, I guess. I'm not sure what that specific application is with like that. Yes?
Yeah, so like when you're talking about nonlinear systems, I was like, when you showed the form, I thought of like Mandelbrot.
Think about what?
The Mandelbrot set.
Okay.
It's like basically the same form. It's just the nonlinearities if it goes from linear or not. So if you want to make like a video to like zoom in on part of it, it's hard to do without like pre-generating all of it in advance. But if you know how many frames you want, you say you want like 10 seconds of it, you can just like make each frame based on like constraining how like precise you need the fraction to be.
Okay. I think that's a separate problem. I'm not familiar with that specific problem that you mentioned. But but I guess this projection is basically just a representation of a set. I guess you can imagine that maybe in terms of a video that you take a 3D object and you're just looking at it from an angle and you see the 2D projection. And then you can, maybe in your camera image, you have depth and maybe you can lift it back up to a different set. But I think that might be something that's quite different from what I'm thinking about. Maybe it's better to talk about it offline because I do have quite a lot of slides to go through. So I will get back to that. Maybe after this, we can talk about it. I'll be happy to talk about it. But this here is just to mention that I guess polytopes can be represented by some lifted intervals. And so if we just compute with intervals, then we get polytopes kind of for free. Okay, so I'm seeing that people have issues with the Zoom. So
Yeah.
what can I do?
Maybe try to
Unshare and reshare, stop sharing and resharing?
Yeah, maybe. Let's try.
Okay,
it looks good
You
now.
good?
okay,
I have a question though.
yes.
So you see the projection, at least on that polytope, it looks kind of, should I say, I'm gonna get that image, but when I live, well, I could get a tube, but why would I get the?
Well, I guess it's just an illustration. I don't have a good picture for it because it's not just lifting, it's lifting and rotating and then translated. So that's what the constraint zonotope is. It's kind of, it has intervals in a higher dimension. That interval is somehow rotated and projected at the same time using a linear map, and then translated. So it's not just like a cylinder or like a rectangle that you have, because there's some sort of rotation involved there, and that's why it becomes a polytope. And then you also have another intersection that cuts through that, and then it becomes a polytope. But it's hard to draw that picture. But that's the best picture that I could try to put together. Okay, let's continue. Okay, the second thing, the next tool that I want to briefly talk about before I get to all the applications is that I guess we want to bound functions where we have functions that are unknown. So if you have functions of the system that you do not know, if you have data points, you can try to interpolate and just, not interpolate, but just fit a function through it. But we want to be able to kind of bound whatever the function is just based on the data that we have. And the way to do it, or one way to do it, is to assume that, or to rely on the fact that functions have some continuity properties. And depending on the continuity properties, we can just take, if you think about it, it has a gradient that has a maximum gradient in this way, a minimum gradient in this way. If you have 2 points, then these are the maximum gradient and this is the gradient. So this is all the possible values that that function could take. And the more data points you have, then you can shrink kind of the set and you get a way to describe or over approximate the function that you have by some set. And so basically just relying on continuity based on different continuity notions, you can get bounding for functions itself, if only based on data. So even if you don't know the function, but you have data and you know some continuity assumptions on them or continuity bounds, then you can bound the function itself also with an interval. Okay. And this here is just an illustration. If I have a certain 3D surface, or I mean kind of a surface here, if I have data, then I can bound it. The more data I have, the closer the bounds would be, just based on continuity. Okay, now let's get, with the very little time we have left, let's quickly try to run through some of the application of the few things that I mentioned and how we can apply that. I'm not able to go into all the details because I'm really behind time, but I just want to mention that we want to do it for control barrier functions. I'm assuming everyone here knows something about control barrier functions. We are just going to assume now that for the safe set, we have an H function that describes the safe set. We assume that that's known. The problem is that we are going to assume that we don't know the function of the system, but we have data. And so we will use the set membership method that I just mentioned to kind of bound the function, and then at the same time trying to bound H dot. And that will allow us to kind of essentially find a way to bound the CBF condition, which is the H dot class alpha, class kappa function of H, for the case when my function is not known. If I use the interpolation method that I just mentioned about just now, you can bound them and come up with some way of implementing it, which turns out to be hard because we have piecewise affine functions. But even though they are piecewise affine, we have a way to decompose it into solving many, many QP problems in parallel, and then just pick the best solution. And that makes it a lot more computationally fast. And there is also some ways of making it faster by leveraging some monotonicity property, but I'm not going to go into that. And if we don't know the Lipschitz constants or the Jacobian bounds of a function, we can also try to learn that and use packed learning type guarantees to give us some notion of how close we are to that learning the constants, continuity constants. This here is just to show some examples, just to mention that our methods are these 4 methods here. Those are much, much faster than the method that we found in the literature that uses the second order cone program. And essentially, the main thing that we can buy from there is that we can solve them all in parallel, and we only have to solve QPs, and we are able to do it a lot faster. And this here is to show that if we do it for adaptive cruise control, we guarantee that the H always remains positive, and so our system would be safe. And if we want to have bounded uncertainties or whatever, we can always use mixed monotone based function bounding that I talked about earlier. Okay, I'm not sure whether I really have time to talk about this here, but this here, I just want to quickly say that we want to train, sometimes people want to train neural networks, feed-forward neural networks or transformers. What people tend to do is when you learn a controller for a plant, you use CBF as a safety filter that you just add on to that after you train your controller. And in those cases, what could happen is that once you add the safety filter, then you don't actually achieve your mission anymore or your task, whatever you control it for. You might get stuck and you never get to where you want to go to. So what we did, or this is a preview of what we are doing, we are trying to add that layer and put it into a way, find a way to put it into, combine it with the neural network so that we can train them together. So that when you train them together, we can guarantee that the CBF condition will always hold. By however you train it, it's going to hold. And then because we are training it to satisfy some objective function, then that doesn't have the same problem that the safety filter can be done. And that relies on this projection that I talked about. And I guess I just don't have time to go through all of this, but just want to mention that our methods allow us to incorporate like CBF, CLF conditions, and even input constraints when we do the training, and we can guarantee that the neural network controller that we design, or however you train it, it will always satisfy the constraints. Okay. Just skip all that and get to the part about state estimation, and then I will take questions. So state estimations. So I guess one thing that I mentioned is that if we have the mixed monotonicity and we have the embedding system that can bound the dynamics of the system, it turns out that you can directly use that to design an interval observer. And not only can you design it to use it to design an interval observer, but you can include observer gains, and you can minimize the estimation error that you have, or the width of the set that you have, such that it's optimal in some sense in terms of the H infinity gain or the L1 gain of the system, where we can actually we've recently found that we can just solve a linear program and manage to get the gains of the observer to make sure that the intervals will always kind of contract. And the way to do it is just to design, use mixed monotone decomposition. It looks complicated because we have some additional transformation that we did to make it more applicable, but essentially it's just applying mixed monotone decompositions. Okay, just some simulations, discrete, continuous, discrete time, and continuous time, just to make sure that the true states are always bounded. So our estimates always gives us the upper and lower bounds of the true function. We can also apply it to hybrid systems. Not going to talk about it, but it applies also to hybrid systems, including a bouncing ball example, where we can handle that as well. Okay, so this is the part that I want to get to, and that's where I will end then, is that it turns out that using this mixed monotone method for designing interval observers is just a sufficient condition, or at least the past designs have been mainly sufficient, meaning that if you can find the observer gain, then your interval observer exists. But if you cannot find it, then you don't know whether it exists or not. And in fact, that even if a stable normal Lindbergh observer or common filter exists, there is no way to know that an stable interval observer would exist or not. So this, I believe, is an open question for quite a while to say whether you can even design a stable interval observer for linear observable or detectable systems. So for linear systems that are detectable, we know that we can just use a Lindbergh observer or common filter type thing. You can always get some sort of a stable observer, but it's actually unclear for interval observers. And in parallel, I guess there's some work that very recently, as of October last year, they found that you can actually do it for linear observer systems. You can find a transformation of the system that is time invariant to be able to do that. But what we found, the work that we presented just in December at CDC, is that actually we can have an interval observer of the same dimension for all linear observable systems as well, which is the same as theirs there. But we can show that for some linear detectable systems, we can do that. And crucially, we can actually do it for all linear detectable systems if we allow us to have lifted states. So to go from the interval to a polytope, because I was just saying that a polytope is just another representation of that is you can think about it as just some lifted intervals that's rotated and being sliced or something. So basically that's the observation. So basically what it's saying is that if you design an interval observer with more states, lifted states, then you can actually design an interval observer, and that was not possible before. And the way we kind of do this kind of lifting is actually just stealing ideas from this norm-based polyhedral Lyapunov function theory and using the transformation that they have presented there. And I don't have time to go into the details, but it can be shown that if you lift it using a P matrix being the transformation matrix that kind of helps you with the lifting, that if you do that, then the interval observer that you design for that based on the mixed monotonicity method with embedding function will not impose any restrictions at all. Okay, I know that went really quickly, but this is some pictures of the interval or the set valued observation that you can have. We start from a big set. Over time, it kind of shrinks up until that set becomes kind of negligibly small, I guess, if you can design an observer for that, for both continuous time and discrete time systems. Okay, so with that, I just want to quickly conclude. I think I spent a lot of time on this, and I think that's great because that's good for learning. For learning what is mixed monotone decomposition functions, how do we construct them, and how do we construct embedding systems based on that? And why? Because it allows us to bound systems or states of systems very easily. And then I also briefly talk about interpolation as a way to kind of bound functions from just data. And then I applied that interpolation stuff to ensure that CBF or safety type conditions can hold even for systems with unknown dynamics, but we only have data. And I kind of give a brief sneak preview of how can you train a neural network to satisfy CBF, CLF, and input constraints all at once. And then finally, I guess we apply that to the mixed monotone stuff to design interval and polytopic observers for linear systems, nonlinear systems, hybrid systems, and shown that we can get set value estimates for all of them. And I guess with that, I just want to acknowledge some of my sponsors for different few projects that I have, as well as all the different students that have worked over the years that have helped develop a lot of this research. So thank you for your attention. I'll be happy to take any questions that you have.
Thank you. So,
Yes,
yeah, go ahead.
go ahead.
Yeah,
Okay.
you're going. Paul.
Thank you. Very nice talk. Personally, I'm most interested in your observer design, but unfortunately, you don't have enough time. So
Yeah, I spent too much time in the first part, and
my question mainly is on the last part of section 2. You're saying that Lipschitz continuous system gonna lead to that convex, but the Holder continuous gonna lead to non-convex. Is that reason?
okay, that's a good question. That is related to I guess I'm not sure whether where is that? Is this specific slide here? Okay, this slide here.
Yes.
Sorry, this here. So basically the reason is because when you try to apply the definition of a Lipschitz continuity, it's just going to be a Lipschitz constant times some sort of a norm of something. And if it's the one norm or the infinity norm, it's just going to be something that you can represent with a linear constraint. But if it's a Holder type of continuity, then you have a power to the norm. And that makes it not as easy to bound them, I guess, depending on what the power is. It could be non-convex. That's my point.
Okay.
Yes,
So it's basically like you're stacking the boxes and sliding them around.
I'm stacking what?
You're stacking like these windows and sliding them around. But that makes sense if you're trying to render a video. But if you're just trying to reduce uncertainty, why wouldn't you use like an ellipse or like a circle?
Yeah, so I guess the ellipse is a valid set representation.
Diffusion. It'd be like a
Yeah, so basically that the main reason maybe it's definitely a valid method to try to just use ellipses, and that's kind of what I was trying to get to with this specific slide here that I have that it's not showing anymore. Okay, it is. That I guess you can compute with ellipses, but there are certain operations when you compute with the ellipse, they don't actually remain ellipses anymore, and you will have to bound them anyway. And ellipses also have the disadvantage that ellipses are kind of more symmetric, whereas polytopes in general can be as asymmetric as you want. So when we are trying to bound them, we're trying to bound them as tightly as possible. If you restrict yourself to a symmetric set representation, then you naturally will have to have a bigger set. And that's one reason. And the other reason is that when you design a lot of the safety control and the observer type methods, whenever you deal with polytopes or intervals, you try to solve things, you end up getting linear programs, which are much easier to solve. And when you start dealing with ellipsoids, you end up usually having to resort to, I guess, SDPs, semi-definite programs, or some form of quadratic QCQP or SOCP type problems, which are optimization problems that are known to be more or slightly more, or in my opinion, harder to solve or more limited to lower dimensional systems. So they are advantageous to computing with intervals because intervals are fast, and they are, with polytopes, it can be more accurate than dealing with ellipsoids, which can be slower and more conservative.
So you mentioned like safety applications. So I assume like when you're talking about a car, like the aperture size also matters.
The what?
The aperture size. So if you take the cube, if you can show like the cube pictures again, there's a lot of wasted space around the corners. But if you were to take like a sphere and just like encase it as close as possible, you waste the least space. So if you're on a car that fits like you have a much wider radius.
So I guess the work that we are doing here is not limited to perception, or so the aperture size it's not a concern here, I guess. I think what you're talking about with aperture size, what it would limit is when you have measurements, the set representation of it will tell us the bounds of the set that we have. And whether it's ellipsoid or interval, it just means that if you have a bigger aperture, then your bounding box might be bigger or smaller. Yes, we can talk about that later.
30 minutes to people that might want to move to their next meeting, and we can continue the discussion here. Like, thanks again, Professor Yu.
Okay. So I guess. Too slow.